Hello everyone, I am Arun Supramanian. Today, I'll be speaking on big data and machine learning in healthcare and how these technologies are driving improvements in diagnostic accuracy, personalized treatment planning, and operational optimization. We will explore the data landscape and scalable processing architectures and the role of machine learning in analyzing patients' data at scale. Healthcare data is growing exponentially. By 2025, it's projected to reach 2,500 exabytes, growing faster than any other industry, including finance and media. Here's the kicker: 80% of the data is unstructured, things like imaging, clinical notes, and sensor data from wearables. The opportunity? Healthcare providers using big data have reported cost reduction of to 20% and improved patients' outcome by 30%. But to get there, we need systems that can handle this data reliably and securely and at scale. Source of healthcare data, let's take a closer look at where this data comes from. EHRs includes patient's history, medications, labs, and physician notes. Medical imaging makes up the bulk of healthcare data by volume. A single radiology department may generate 100,000 images daily. Genomic data. Sequencing costs have dropped from 10 million to 1,000 USD, but each genome still adds 200 plus GB of data. Wearables collect 10 to 20 biometric points per second, generating 5 to 15 MB daily per person. That's a massive stream of heterogeneous data, right, for ML, but challenging for traditional infrastructures. Three core challenges define this space: data heterogeneity and volume and velocity and data quality issues. Let's go one by one and explore this. Data heterogeneity. Structured databases, free text nodes, time series vitals, and images all coexist. About 80% of the unstructured and meaning SQL alone won't cut it. A single 300-bed hospital might generate 50 terabytes per year from EHRs. ICU monitors can emit 2000 plus readings per second. Data quality issues. For instance, smoking status is missing in 60% of records. Diagnosis codes vary between hospitals. We need smart pipelines, fault-tolerant systems, and flexible schemas to make sense of this chaos. So here's where scalable data frameworks enter. Apache Spark provides in-memory processing ideal for large-scale batch and stream processing. One provider reduced training time for clinical models by 85% after moving from disk-based system to Spark. AWS Redshift supports petabyte-scale queries and cost-effective storage. A hospital in Germany reported 40% of infrastructure cost savings after migration. Hadoop handles semi-structured and unstructured data. A public health network used it to integrate radiology scans and clinical notes from 10 plus hospitals, enabling ML-based triage support. These platforms are the foundations of modern healthcare analytics. Cloud-based healthcare data lake. The traditional warehouses force early schema decisions, but in healthcare, where data types are dynamic, we need schema and read flexibility. Cloud-based data lakes solves that. They consolidate structured and unstructured sources, supporting 7x more data formats than legacy systems. One US network built a data lake that combined imaging, EHRs, and real-time telemetry. Result: the analytic pipelines that once took days now run in under an hour, and dashboards refresh in real time. The ETL processes in healthcare aren't just about moving data. They are about preserving clinical meaning. Steps include extraction from different systems, normalization using SNOMED, LOIN, and RxNorm, data quality validation to catch missing and inconsistent entries, transformation for models readiness, and incremental loading to support the streaming data. Efficient ETL reduce pipeline latency from 2.5 days to 11 hours at one hospital, resulting in real-time alerting for critical care. ML is reshaping how clinicians are making decisions. A deep learning model for 30-day re-envision predicted achieved an AUC of 0.87, outperforming traditional models. Disease risk models predicted diabetes at 94.3% and heart disease at over 90% and various cancers with up to 96% accuracy. For deterioration prediction, LSTM networks trained on ICU time series data flagged patients decline 6 to 10 hours earlier than manual methods. Hospitals using these tools are seeing fewer readmissions, better outcomes, and improved resource allocations. Medical imaging is a prime area for ML. CNN detect lung nodules on X-rays shows sensitivity and specificity comparable to the expert radiologist. Unit architectures enable anotypical segmentation, reducing manual processing time by 60%. In one pilot, AI-assisted radiology system helped clinicians detect pneumonia in chest scans with a 9% boost in diagnostic accuracy. These tools accelerate diagnosis, improve precision, and help radiologists manage increasing workloads. NLP helps us tap into rich but messy free text data. NLP engines extract structured insights from discharge summaries, pathology reports, and clinical notes. Clinical trial matching platforms now automate patient enrollment using NLP, reducing search times by weeks. Adverse event detection using NLP saw recall rates jump up 25% in one hospital. One model achieved F1 score, so over 0.90 for extracting medication, dosage, and side effect information. This enables real-time text-aware analytics that complements structured records. But it's not all smooth sailing. There are some limited implementation challenges for being security and privacy. Over 60% of healthcare breaches stem from access control misconfigurations. HIPAA demands multi-layer protection, encryption, role-based access, and audit logs. Workflow integrations. Doctors already spend 2 to 3 hours on EHRs per hour for patient care. Any tool must integrate seamlessly into their workflows, ideally within existing systems. Ethical oversight. We need transparency. If a model denies care or gives poor recommendation, we must know why. This means explainable AI and clearly defined accountability structures. Engineering AI for healthcare means building for trust, transparency, and clinical usability. So, to conclude, big data and machine learning are transforming healthcare, but their success hinges on robust, reliable, and responsible systems. And we are uniquely positioned to enable this future, ensuring performance at scale, enforcing security, and keeping patients' outcome at the center. Thanks for the time.